Section 2.4, chemical formulas, is where we're going to start to put those chemical symbols, the letters of chemistry, and start making some words out of them, knowing how to put them together correctly. And as we'll see, there's a couple of types of different formulas that will be introduced here in 2.4. The first is a molecular formula. And all formulas are representations of molecules or compounds. What does a molecular formula have? Well, it has the chemical symbol from the periodic table to indicate the type of atoms that are present. And then it has a subscript after each of those symbols to indicate the number that are present, okay, of that type of atom. Anytime we have more than one atom in a compound or a molecule, we're using a subscript. But if there is only one, that subscript is omitted. Right? We see here, we never write C1. If it's one, you just leave the subscript out. And so if I say H2O, CO2, C6H12O6, CH4, those are all examples of molecular formulas, which are also used as abbreviations for names of compounds at times, right? Sometimes you might just say quickly CO2 instead of carbon dioxide. We also have structural formulas, which gives the same information as a molecular formula, but it builds on it one step further because it also shows how the atoms are connected to one another. And so it actually shows the bonds. And we can see the difference in these two right here. Okay? The compound name on the left, the molecular formula in the middle, and the structural formula on the right. Okay? So the molecular formula, again, symbol, subscript, and notice this slide does have a typo. That should actually be a 4 right there in the middle. Okay, don't let that throw you off. That's a typo from the textbook. And then the structural formula over here, which also tells you the atoms that are present, the number, because you can count them, but also how they're bonded. Every line represents a single bond, and a double line like that represents a double bond. If you ever see 3 lines, that's a triple bond. The lines represent bonds that hold the atoms together. So the structural formula gives you a little bit more information than does the molecular formula. Okay. There are other types of formulas as well, right? Ball and stick models, these you'll see in chapter 7 are really useful for showing molecular geometries. And then a space filling model over here, letter D, which are really useful for showing things like relative size and molecular dipoles, which we'll also talk about in chapter 7. So what else do we have from this section? Okay. We alluded to in chapter 1 the fact that some things on the periodic table aren't just atoms. Okay? They actually exist as molecules. There are several atoms that exist as molecules. Okay? And there are 7 molecules that are known as diatomics because they always come in a pair of 2. Okay? So listed in the middle of this slide here, slide 60, are the 7 diatomic molecules: hydrogen, nitrogen, oxygen, fluorine, chlorine, bromine, and iodine. And you can remember them however you want. I have added here Hofbrinkel, or other people I've heard from high schools use Brinkelhoff, just a quick mnemonic to help you remember these things. Okay, but you do have to know those diatomic molecules for your test. And some things on the periodic table are even higher order molecules. Right? Sulfur exists as S8, for example, which we have on, oh, I skipped right over it, which we have on this slide. Phosphorus exists as P4. And know what those subscripts represent. Right? If I take hydrogen, for example, it's a diatomic. It exists as H2. So I refer to it as one H2 molecule. If I say just H, that means a single atom of hydrogen. 2H means 2 hydrogen atoms because it's 2 individual H's. That's called a coefficient when it's out front. Okay? The subscript means they're together in H2 molecule. I have 2 H2, then I've got 2 H2 molecules. So you have to make sure you're careful and you're paying attention to where that number is. Okay. So the next thing that we're going to address is how do we describe compounds? There's a molecular formula, and there's also an empirical formula, which we'll see in chapters 3 and 4 is really important. What an empirical formula is for a compound is it tells us the types of atoms that are present in the simplest whole number ratio for atoms in a molecule or ions in a compound. That's an empirical formula, the simplest whole number ratio. Okay, so C6H12O6 would be a molecular formula, but the simplest ratio is CH2O, right? C1H2O1, 1 to 2 to 1, the simplest ratio. Okay, and that's elaborated on further here, right? Empirical formula, simplest whole number ratio of atoms or ions. Molecular formula tells you how many are actually present. Another example there with benzene, showing the difference. Keeping in mind, they always have to have whole numbers. You will never see a subscript that is not a whole number. And it is possible for them to be the same. Okay. Carbon dioxide, we've used as an example a couple of times. CO2 is the molecular formula. It's also the empirical formula because you can't get a simpler ratio than 1 carbon to 2 oxygens. Over here, we see vinegar, acetic acid, right? C2H4O2. And that again has an empirical formula of CH2O. If you're given the molecular formula, it's easy to determine the empirical formula. You just look at the simplest whole number ratio. It's harder to go the other way. If you're only given the empirical formula, you need more information to determine what the molecular formula is, and we'll do that in chapter 3. We finish with the idea of isomers and enantiomers in section 2.4. Isomer is not to be confused, you see in the note there on the bottom, with isotope. Isotopes we covered previously. Same number of protons, different number of neutrons. That's an isotope. An isomer, it refers to molecular structures. Okay, it's 2 isomers are 2 compounds that have the same exact chemical formula, but they're bonded differently, meaning they have different molecular structures. Okay. So if we take acetic acid and methylformate, okay, they're shown on the next slide here. They're both C2H4O2. Okay. Notice they have the same exact molecular formula, but they're put together differently. They're bonded differently. That means they are isomers. And they have very different properties, even though they have the same molecular formula and the same empirical formula. These are called structural isomers. They have different types of bonds. There's also something that's known as a spatial isomer, or an enantiomer. And these actually have the same molecular formula, the same empirical formula, and they're bonded the same. They're just different in 3 dimensions. They're called non-superimposable mirror images, okay, which are like your 2 hands. They're mirror images of one another, but you can't put them directly on top. That's the non-superimposable part. And so here we see 2 enantiomers. Everything's the same, even the bonding. They just differ in the placement in 3 dimensions. Okay. And those are called spatial isomers. That's not something you'll be responsible for in general chemistry, but they're an important topic in organic chemistry. So that wraps up section 2.4. Okay, know what isomers are, know molecular formula versus empirical formula, and know structural formula versus molecular formula, and all the information that they give you, what a coefficient means, what a subscript means, and remember those 7 diatomics.